So if we open up the velocity of the planet is omega of the planet. So what do we have? Omega planet is equal to omega of the ring, which is 3 radians per second, times 40 plus 160 millimeters over 80 millimeters. So that's equal to 6 radians per second. So the planet is going twice as fast as the ring in this case. So now we know omega of the planet. How do we figure out the omega of the arm? Well, we need to have a point on the arm which has the same velocity as someplace else. Where is that? The center of the gear. Let's say point C. So we know that the velocity of C on the arm is equal to the velocity of C on the planet. What's the velocity of C on the arm? It's omega arm times what?
3.
What's the distance?
120.
120. It's 80 plus 40. 40 millimeters plus 80 millimeters. And that's equal to what? Velocity of C on the planet, what's that? Well, where on the planet do we like the velocity? It's the ground here. And so it's going to be 40 millimeters times omega planet, which is 6 radians per second. So from here we get the omega arm equals 2. It's 40 over 120 times 6, which is 2 radians per second. And all of our radiuses were pointing up. What would happen if a radius was pointing down? What would happen if the ring was fixed? Then what happens? Then this would be fixed, and this wouldn't. Then we would have the omega of the sun going this way, and the planet would be going. The radius would be going the opposite way. And so, where is the? It made it all the way around. Right. So if we hold the ring fixed, then the planets are rotating the opposite direction as the sun. The arm is going the same way as the sun, but the planets are going the opposite direction. Because the radius from B to A is in the opposite direction of the radius of origin to A. So since the radiuses are in the opposite direction, then the omegas also have to be in the opposite direction. This is basically what we would have there. So that's the problem we didn't get to at the end of last class, and I think, will that help you on the homework? Yeah. So I realized that I posted the answer, but it's a little harder to figure out unless you've done it before. Now, so that was one way of looking at velocity, the relative velocity. There's a magic point. Our magic point that we liked on our gears is the point that has 0 velocity. It turns out for any link that's rotating, there can be a point on it, or any object that's rotating, if you extend it, there can be a point with 0 velocity, and that's the instant center, and that's what we're trying to find today. Were there other questions over the homework, or? No? Okay, so that was the first activity. First question?
Sorry, the one with the hole and the wedge one underneath it.
A hole.
Number 6.
Number 6.
Number 6. Which is what?
6 point.
It's in the book?
No, I don't know.
Yeah, it's
6
16.5, 16.52.
Did I get it right? 16 point, okay, and then my book. Good day. .52, you said?
It's one of the last problems in 16.
That's 16.5.
Okay. And this was under absolute motion. Okay. So this is given this phi, and this is theta, right?
Length of the polar.
And L. And this is X, and this is whatever.
They have V going.
What?
V is going to the full side of the X to the left.
This is V, and this is whatever, Q. Right, so what is V?
Is it cosine? V cosine.
V is, you can relate V to X, right? V equals X dot. So now you have to relate X to phi somehow by geometry. You might want to do it by a Q or by your height. Basically what you want to read it.
And then is that the hard part or?
Then you take the derivative. Right?
Well, it's good at asking for the omega.
Yeah. What's the so we need to relate X to theta, and once we take the derivative, we get X dot to theta dot.
Would you relate X to theta using the law of cosines, or would you do it a different way by using like geometry or trigonometry?
I would probably figure out what the height is.
But the height's changing too, right?
The height changes too. The height you can relate to Q, or you can relate the height to your position, or you can relate Q to your position, and you can relate Q to theta. So that's basically what you want to do is you need to somehow relate Q, X dot to theta dot, and Q is what's changing. And so either the height or Q you can relate to X, and then once you get that, then it's easy to go from Q to theta using the law of sine. Yeah, that's the secret, is to get the position. Once you have the position, it's not very hard. All right, let's do that special point. Actually, do the quiz. So, instantaneous center can be used to determine the something of any point on a rigid body. All right. everybody. So this is another velocity analysis method. So you can use relative velocity or you can use instantaneous center. Instantaneous, that's the second question. The velocity of a point on a rigid body is something to the relative position vector extending from the instant center to the point. Seconds. All right, and that's V is equal to R omega, and it's always perpendicular to R, so that would V. So basically, once we find the instant center, we can use that to visualize in our brain how things are moving. And so here's an application. The instant center, if a wheel is not slipping, is always the point of contact on the ground. This is also true for gears. So the velocity at any point in the rim is always perpendicular to the radius from the instant center to the rim. Where is going to have the maximum velocity? The top, which has the maximum distance from the instant center. I don't like that second question. Yes?
Is that relative?
It's relative, but the relative is the instant center of the velocity is 0, so it's the absolute velocity as well.
Okay.
And this is very useful for what? What uses velocity in our toolbox?
Energy.
Energy. And so we don't have to figure out all the complicated kinematics. For acceleration, we can just use velocities when we're dealing with energy, which light is good. What do we have? The board is sliding down the wall. General plane motion. So one way we dealt with it is basically we can figure out what x is, what y is, take the derivatives. One way is that BB is equal to BA plus BB with respect to A. That was what we did last time. And now we figured out that we can figure out that the instant center is going to be here. And based on that, we can figure out what the omega of our rod is. And then figure out what the velocity of V is going to be. If we know that this point has 0 velocity, how can we figure out the omega of this rod? If we know VA, it's V times the distance, or V divided by the distance is omega. The velocity is the distance times omega, and it's the distance from the instant center to point A. The instant center isn't on our rod, but it can be used to analyze our rod fairly quickly. What is the direction of the velocity of the center of gravity of the board?
You have to try.
Well, here's the instant center. So here's the radius from the radius to the instant center. And so it's going to be perpendicular to that. Right? We didn't have to do any calculations, but now we know that the center of gravity is moving down into the left, assuming that we're going down. So any point, any body in planar motion, there's always a point that has 0 instant velocity if it's rigidly connected to the body. And this is the instant center, and it may or may not lie on the body. Just like the yardstick example, the instant center wasn't on the body, so we're assuming it's magically connected there by some inextensible object. And basically, the velocity is simplified because our V is equal to VA plus VB with respect to A. VA, what's the velocity of the instant center? 0, just like we had there. That's our happy points, or the points where velocity is equal to 0. And so therefore, the velocity analysis is simplified. We don't have a nice matrix equation. So at any given point, if we know the omega and we know the velocity, what do we know about the instant center? Well, it's somewhere along this line right here, right? Because we know that the velocity is always perpendicular. V is equal to R times omega, and it's always perpendicular to R. So we know that the radius is somewhere along this line right there. If we know the velocity and we know the omega, what is the distance? It's the velocity over the omega will give you your distance. So if we know velocity, we know omega, then we can figure out what the radius is going to be, that it's V over omega. So that's one case. What's another case? If we know that the velocity of A is down like this, if we know the velocity of B is down like this, what do we know about the instant center?
Put it across.
Well, the instant center has to be on a line perpendicular to RBC, because we know RBC is perpendicular to BB. It has to be somewhere along this line here. Similarly, we know the velocity of A is down and to the left, and so the instant center has to be somewhere along this radius here. And so where's it going to be? That's the intersection of the 2 points where the velocities are going to cross. Similar case, now we know BB is horizontal, BA is vertical. Where's the instant center going to be? Well, somewhere along the line, and so then we can figure out what omega is. It'll be in between. If they're both going in the same direction, then basically we can use triangles or to basically figure out what the instant center is going to be here. If BA is equal to BB, then where's the instant center? Not at 0, at infinity, right? Because what would happen? Where would this line intersect the vertical line? If these were the same, it would be parallel, and so it has an infinite instant center. So what's omega going to be?
0.
0, because B is equal to R omega. R is infinity, so B has to be 0 so that mathematically you don't get infinite velocity. So once we know the instant center, then we can figure out the velocity of any point on our object. It's just the radius or the distance to the instant center times the velocity. So we're basically rotating. Here's your omega. The easiest way to do it is to write your omega about your instant center, so you can figure out where everybody is going to be rotating about. All right, let's see if we can do an example, if that will help clarify things. So here we have a simple piston type arrangement system like a piston in your engine. What we want to figure out is the velocity of lengths AB and BD. So if we draw this out like this, and like this is 0.4 meters, this is 0.4 meters. This, at this instant, is 90 degrees. And we know that the velocity of our piston is 3 meters per second. So we want to figure out what the velocities, angular velocities, are of AB and BC. And we want to use instant centers to find this because this is our new technology. We could have done that velocity of C is equal to the velocity of B plus the velocity of C with respect to B. That would be what we would do from last class. But now we want to do the same problem but use instant centers. So, what's the instant center of rod AB?
Oh, no, point A.
AB. What's the point on rod AB that has 0 velocity?
Point A.
Point A. That's very easy to find. Now, on BC, it's a little harder to find. What do we know about the velocity of B? Well, since this is an instant center, it's basically going to be going down or, right? So this, assuming that this is omega AB, then we're assuming our velocity is going to be going up and to the right. What do we know about our instant center? So this is velocity of B. Well, we know that the instant center has to be if this velocity is horizontal, then the instant center has to be somewhere, the radius has to be somewhere perpendicular. So the instant center has to be somewhere along this line, right? Because the radius has to be perpendicular to the velocity. What else do we know about the instant center of BC? Well, it has to be perpendicular to this velocity too, which means it has to be along the link, because this velocity is perpendicular to this thing, so it basically has to be along that. So where is the instant center going to be?
Intersection.
Hey, cool, here's the instant center. All right, if that's the instant center, what's our geometry? What's this distance here? This is 0.4. What's this distance here? 0.4 square root of 2, because this is nice, 45, 45, 90 triangle. Okay, and so we're assuming right-hand rule. So basically what we get, this is omega of BC. Before we were writing it about B because we were to say the velocity of C with respect to B. Now we're taking all of our velocities relative to the instant center. Why? What's so cool about the instant center? Velocity is 0, and so therefore we don't have to deal with those relative velocities anymore. And so basically what do we get? We have the velocity of C is equal to 3 meters per second. What is it on length BC? Well, the velocity is equal to r omega. And so r is equal to 0.4 square root of 2 times omega BC. What direction is this velocity? 3 meters per second is given to the right. What direction is this velocity going to be? As we assumed a right-hand rule, so we're rotating around like this, and so you follow the arrow, and it's also going to be to the right. Which means our negatives are, we don't have to worry about negatives, everything cancels out. And so basically what we get is omega BC is equal to 3 over 0.4 square root of 2. And this is that's meters, so this is meters per second over meters, gives us 1 over seconds. And I can't do 1 over seconds in later. It's 5.3 radians per second. Okay, so that's B, and now velocity of B is on both AB and BC. What's the velocity of B on BC? What's the velocity of B? It's r omega, so it's 0.4 meters times 5.3 radians per second. What direction is that going to be? Down and to the right. We're rotating about here, so as we're rotating around, velocity of B is going to be down and to the right. That's equal to, it's also, point B is also on AB. What's the velocity of B on AB? It's r omega, so it's 0.4 meters times omega AB. What direction is that going to be? That's how we initially assumed it. That's going to be up and to the left. And so therefore we get that omega AB is equal to minus 5.3 radians per second. So it's equal to 5.3 radians per second. This omega 5.3 was counterclockwise, so this would be 5.3 clockwise. And that's just at this instant. Later on, our instant center is going to move, and we're going to have to do a new drawing. But at this instant, basically omega AB and omega BD, oh, it's D, sorry, have the same velocity.
Would the omegas be constant throughout the whole?
No, the omegas are going to change as we're rotating.
So the instantaneous center changes and the omegas change.
Yeah, it's basically at this instant, it's going to change. I mean, this is what it is at this instant. Later on, it's going to be flat. And so, yeah, it's basically visualizing what's going on. All right, question, answer? What about this example? Where's the instant center? Point of contact. Right, we have a wheel rotating. This is C. This is A, and this is B, and we're basically rolling about this, it's a small wheel with a big wheel in between it, or actually two big wheels and the small wheel rotating on a shaft. And then what we're given is that the velocity of point C is 2 feet per second. We have this is 3 inches, and the big radius is 8 inches. So we know our velocity. What are we trying to find? The velocities of point A and B at the instant shown. So, using the concept of instant centers, where are we rotating about? Where do we write our omegas about? At the point of the ground, right? So this is now omega. Omega is written about the constant, and so the velocity of C we're given is 2 feet per second, which is 24 inches per second. Since everything else is in inches, and that's to the right, and that's equal to what? R omega. What's R? 3. R is the distance from the point of zero velocity, that's our instant center, to the point of interest, which is C. So 3 inches times omega. We just have one omega because we have only one body. What direction is this going to be? We're assuming that this is going to be to the left. We assumed omega was counterclockwise by the right-hand rule. And so this point C would be moving to the left. And so therefore, we can figure out that omega is equal to negative, because this is opposite directions, 8 radians per second. So that's the velocity of C. Based on the velocity of C, we figured out what omega is. Next, how do we figure out the velocity of B? Well, it's just equal to R omega. It's equal to, what's the radius?
11.
It's 8. It's 3 plus 8, so it's 8 inches plus 3 inches times omega, which is minus 8 radians per second, and that gives 8 plus 3 is 11. So it's going to be 88 inches per second to the right. Because your R omega, we assume, is going to the left. And so that means that the top is moving a lot faster than the center in this configuration. What about the velocity of point A? Question?
Why is it going that way? And it shouldn't be going out?
No? You need to get the yo-yo out. Here's a proper chart for this situation. So basically, the point of contact on the ground is fixed, and then as the center moves to the left, the velocity of the top is also moving to the left. It's moving actually a lot faster. The top is moving a lot faster than the center.
So I was just wondering what happened to that negative sign.
That negative sign, well, positive, this still has, so this is, right, the R omega, assuming we're rotating omega, B is moving to the left.
It's negative.
And so it's negative, negative to the left, which means it's positive to the right. Which is, I wave my hand over. Okay, what about the velocity of A? What is your R? This is now your R. So R is 3 square root of 2 omega. What direction is that going to be going?
Downward, right?
Well, just from R omega,
Down to the right.
it's going to be up and to
Oh, yeah.
the left, and omega we had was minus 8, and so we get 24 square root of 2 inches per second, and that's going to be going down and to the right.
Wait, why did you say that that one's going up and to the left?
If we have, this is our situation here, we're rotating about this point with the omega as we've defined, and this point here is going to go up and to the left. This is our radius, this is omega, and so as we're rotating around this point, then point A is going to be going up and to the left.
Okay.
So that's what, by what we call positive, this is what we call positive, and so what we get is a negative number, and so it's going to be going down to the right. Life would have been a lot easier if I just would have assumed that we'd be rotating.
So we realized that the assumed direction for the omega was wrong. We're going the
Correct.
other
We assumed we were rotating clockwise by the right-hand rule, not because we looked at the problem. So as long as you stay consistent with your assumption all the way through your problem, you end up with the right answer. So when you change the direction of omega, you have problems. All right. Velocity of 2 points on a body are equal in magnitude and parallel, but in opposite direction. Where is the instant center? All right, 5 more seconds. 3, 2, 1. All right, draw a picture. So what are they? They are parallel, same magnitude, but in opposite directions. Where's the instant center? Right, you connect the dots, and so the instant center is in the middle. If they're in the same direction, then the answer would be A, infinity. But when they're in opposite directions, the answer is C, midpoint. All right, now we're voting. Okay, let's get something new to vote on. When the direction and velocities of 2 points on a body are perpendicular to each other, draw a sketch that might help. Where is the instant center? So there's your picture, if that helps. All right, 10 more seconds. Where's the instant center? Well, it has to be perpendicular to this line. It has to be perpendicular to this line, which is none of the above. It's not at infinity, it's not at either of the points, and it's not at the midpoint. And so D is the right answer.
It could be at one of the.
There is a special case, yes. If this was VB, right, then it has to be along this line and this line. And then it could be at one of the 2 points.
Okay.
But that's a
Special.
very special. It doesn't happen. All right. I don't know if we'll have full time to solve this problem, but at least we'll have a chance to figure out where the instant center is and what our equations are going to be. So our points are A, B, C, and D. This is 30 degrees. This is 0.6 meters. This distance is 0.3 meters and 0.3 meters. And yeah, this is aligned with that. And so what we're trying to find is, we know omega CD. So we're given omega CD is 6 radians per second. We want to figure out what the velocity of point E is and the omega of AB. So how would we go about doing that? In the time remaining, 5 minutes, I don't think we'll get this with numbers.
Just be the same velocity C is D.
No. So.
C equals R.
BC is R omega, but both C and E and B are all moving. And so it's just not R omega plus the other one. So what do we know about the velocity of point C? It's perpendicular to D. And so this velocity of C equals 6 radians per second times 0.6 meters, because point D is the instant center for BC. What about link AB? Any instant centers there? Hey, point A is an instant center, so this is an instant center. Therefore, what do we, so we always draw our omega. This is omega AB. Always draw it about the instant center, then you're less likely to confuse yourself. So what do we know about the velocity of B? Right, it's going to be perpendicular. So this is the velocity of B on link AB. So now where is the instant center on link BC? Well, we know it has to be somewhere along perpendicular to here. Right, because it's perpendicular to this velocity, or somewhere along this link, because this velocity is perpendicular to this link, and has to be perpendicular to, or along DC, and so this is the instant center on BC. What's this angle right there? 30. 30. Very good. My green is not too good. So, geometry. What's this length?
1.2.
It's 1.2 meters, right? Because the 30, 60, 90 is what, 1, 2, square root of 3. So therefore, that's 1.2. What's this distance here? 0.6 over the square root of 3, because this distance here on this triangle is square root of 3 times this distance there. So it's 0.6 square root of 3. This distance is 1.2 over the square root of 3. So, where do we write omega BC? We're rotating about, so this is omega BC.
I think that's gonna be negative because both those are going out, right?
Oh, we assumed a direction for this, but yeah, with this assumption here, we don't know what this is. But this one we do know it's going to be. So we look at it and we say, oh, we assumed the wrong direction. How do we know it's rotating in the opposite direction? This radius is the opposite direction of this radius. And since it's omega cross r is your velocity, if the radiuses are in the opposite direction, then the omegas are going to be in the opposite direction. So what do we get? We get that the velocity of c is 6 radians per second times 0.6 meters. And that's going to the left is equal to the radius 0.6 over the square root of 3 times omega BC, and that's directed, with this assumption, it would be directed to the left, so therefore we get omega BC is equal to what? 6 cancels with the 6, and so we get 6 square root of 3 radians per second. And it's negative, so
But that'll be going which direction?
so it'll be going,
Yeah. Clockwise.
it'll be going clockwise, which is 6 square root of 3 clockwise.
Wait.
Okay.
That's counterclockwise. My clock is upside down. I'm on the wrong side of the clock. I'm in the clock looking out. Okay. How about the velocity of B? Velocity of B is equal to 1.2 over the square root of 3. Using this assumption of the omega would be down and to the right, and omega is 6 square root of 3, and that would be negative. And that's equal to 1.2 times omega AB, and that we assumed is going to be up and to the right. So therefore we get that omega AB, viewed in opposite directions, this is negative. 1.2 cancels out with 1.2, square root of 3 cancels out with the square root of 3, so it's equal to 6 radians per second.
In the direction we wrote.
In the direction we wrote. Counterclockwise. Here's one negative and here's the opposite direction. All right, so what's that R? I don't know what that R is. But basically the velocity of E is going to be going R omega down like that. And that's the challenge of that. And I am over time. Is there travel today? No, that's why you guys are
more patient than usual.
Careful, I gotta get out of here. Yes. Hector wasn't here. No one else?